Okay. Sequence. What's a sequence? Huh?
Pattern of numbers.
What he said. Okay. A pattern of numbers, okay, whose domain is the positive integers. That's important. Okay. We're going to denote sequences two different ways, either f of n or a sub n. A sub n. Which is what you're used to seeing it as. Okay, you don't have to write these down. We can just look at them. Here's a nice geometric series. You flash back to pre-calculus. Okay, everything is from term to term. We're multiplying by 2. Right? Here is a okay. Here is a sequence. 1/2, 2/3, 3/4, 4/5, 5/6, 6/7. Here's another geometric series where everything's getting multiplied by 1/3 from term to term. Okay. This is actually a sequence 1, -1, 1, -1. Okay, it's just alternating between 1 and -1. Okay. If we were to write this one, do you remember how we do it?
-1 to the n minus 1.
You could say n minus 1 or you could say n plus 1. Either one would work. That way when you plug in 1, you get something squared, positive 1. You plug in 2, -1 cubed is -1, etc. Okay? All right. So what we care about is whether our sequences converge or not. What does it mean to converge?
Like we get closer to one certain value.
Okay, good. It means we're approaching a value. So, first of all, the limit of a sequence, we literally take the limit of the rule. We get a value. If we actually get a value, that means it converges. If we get like infinity or negative infinity, we say that it diverges.
I'm guessing you know it means like infinitely or something like that.
So more than the 1 -1, that's the divergence.
It was.
Would it be something like a second? Or a second?
Well, I mean, you could think of, you could write that sequence as a sine or cosine sequence. Yes. Huh? Well, yeah, you could write it either way. Like you could write like sine of cosine of pi x, and then you get the 1, -1, 1, -1, 1. All right. So this sequence: 1/2, 2/3, 3/4, 4/5, 5/6. Zach, how would we write that sequence?
N divided by plus 1.
Does that make sense? Everyone else? N over n plus 1. So then what we can do is we take the limit as n approaches infinity of n over n plus 1, which is okay. I don't think so.
Okay, because we're not taking the sum, we're taking the last value. Okay.
What are the values going to approach? Now, the sum, that's a series. That's what we talk about for the next 2 weeks, okay? But as far as the sequence is concerned, the sequence is going to converge to 1, which means as we look at the terms, the terms are going to get closer and closer and closer to 1 the more we go out. That's what that means. You need laboratory drill for that one there, or knowledge of horizontal axis. Okay. Next sequence. Rewrite this. Jeff?
1 over 3n, 1 over 3 to the n.
If I plug in 1, we would start at 1/3. So let's change the exponent to n minus 1. That way when we plug in 1, we would start at 1. When we plug in 2, we have 1/3, etc. Does that work for you?
Wait, so we start at 1?
Mm-hmm.
Okay.
Would it be easier to do 1/3 all of that to the n minus 1?
You can do that too.
Would make it easier.
You think that?
It's more like a notation.
Both ways would be acceptable. When we get into geometric sequences, we would write it as 1/3, all of it to n minus 1. Okay, but to take the limit, it might be easier. Think of it like this. What's that limit going to be? Sammy? Yes. So this sequence converges to 0. The farther we go out, the closer our terms get to 0. Tomorrow we'll talk about what that sum will converge to. Okay, is the converse true? Okay, basically we said that if the limit exists, then that means it converges. Okay, so what if the limit, so, what am I trying to say? What if the limit doesn't exist? Okay, so just because our sequence converges doesn't mean the limit's going to exist. That's the converse. So if the limit exists, our sequence is going to converge, but going backwards is not necessarily true. For example, we have this right here. What's that going to get closer and closer to? 0. This is going to converge to 0, but the limit doesn't exist. So going backwards is not true. Okay? Not really something that we have to worry too much about. Let's talk about some properties of limits. When we're working with sequences, these are properties of limits that we can use. Okay? Like always, if there is a constant, we can throw it outside. Remember, these are for convergent series. If there's adding or subtracting, we can split it into 2, like always. If there's multiplication, we can multiply the 2 limits together. Granted, they're both convergent, right? Okay. And the last one involves division. Okay, we can divide the 2 limits as long as that denominator is obviously not 0. Sean, have you seen Bailey at all?
I don't know.
Okay, I didn't know if you saw him as you walked in. Okay.
He is a first starter, so
Right.
I don't think anybody hears it. I guess you could like check this out.
Well, because he's not marked as being gone, so that's just
I don't-
okay. As we mentioned before, okay, if a series does not converge, then we say, or excuse me, sequences. If a sequence does not converge, then we say that it diverges. Okay, we talked about that with the 1, -1, 1, -1. That one's not going to have a limit, so we say that the sequence diverges. Okay. We need to talk about a couple terms. Okay. Monotonic. Anybody remember what monotonic is? One tone.
Sequence of only a single number?
Huh?
Sequence of only a single
No, it would not be possible. Because a sequence has a domain of all positive integers. Okay. A sequence is monotonic if it is non-decreasing or non-increasing. Okay, and there's a whole name that sounds kind of strange. A non-decreasing sequence would look like this.
It would be a flat line looking at it graphically.
Well, basically, it's either flat or increasing. From term to term, they're either the same or they are increasing.
That's, he says, essentially that's not increasing
Non-decreasing.
and not increasing.
Then this is a non-decreasing. This would be a non-increasing.
One or the other, or both.
What's the meaning of
I
that?
said it has, or,
It has to be either decreasing or increasing, or neither.
So basically here, we're increasing, here we're decreasing. And it's okay if from one term to the next they're the same, basically. Think about it, if all the terms are the same, we can figure out what it's converting to, right? Okay. Monotonic, non-decreasing or non-increasing. Now, let's talk about a bounded sequence.
Majority of, I think it should be being monotonic, like n over n plus one.
Right, that's monotonic, but then there's like one, negative one, negative one.
Oh, I see, okay, I see.
Okay. Bounded. Describe it to me.
Maybe increase by one, but they stop at a certain point.
the range is set.
Okay, the range.
The
Like
range
caps
is
out.
fine.
Okay. Okay. Anything else that you're out there? No, you're not wrong. Okay. If we're bounded, above, then that means every term in our sequence is less than or equal to some value. Okay. If we're bounded below, jeez, I can't write them. And that means every term in our sequence is greater than or equal to some number. If we call our sequence bounded, then, well,
So it's basically like a horizontal class.
yes. Hmm?
Can we be double bounded?
Yeah.
Yes. We would just say bounded. Okay? If our sequence is monotonic and bounded, what will that mean? Yep. Makes sense, right? Okay. Now, don't write this down, but let's just think about what this would look like. Okay? If we have an increasing sequence, then a sub n is always less than a sub n plus 1. Right? We have a term that's always less than the next one. If we're decreasing, then a sub n is always bigger than a sub n plus 1 all the time, no matter what. Right? Okay. If we are non-increasing, that means we are decreasing, but we could have equality from term to term. If we are non-decreasing, then we are increasing, but could have equality from term to term. Okay? All of these are describing a monotonic sequence. Okay? Either purely increasing or purely decreasing. That still counts as monotonic. Non-increasing, non-decreasing, obviously is the definition of monotonic. Okay, now, we need to be able to determine if a sequence is increasing or decreasing. Okay.
Nothing at the school works.
Okay, we need to be able to tell whether a sequence is increasing or decreasing without having to write out all of the terms, okay? This is something that we're gonna do right now, and we're gonna have to come back to it later when we're talking about one of our special rules for converging series. Okay? We're not gonna graph it. Okay, there's a few tests that we can do. The first one is the difference test. Difference means what? Okay, if we subtract a sub n plus 1 minus a sub n, and it's larger than 0, then our sequence is increasing. And this is in general. This isn't taking 2/3 minus 1/2. This is taking a sub n plus 1 minus a sub n.
Would it be greater than equal to 0 or just greater?
Great. So this is purely increasing and decreasing.
Okay.
This isn't non-increasing. Okay. What about if we wanted to use the difference test for decreasing? Then it would be, yes, less than 0. A sequence is increasing if that difference is less than 0. Yes.
Under some things that are greatness rules, like n minus 4 all which is squared.
Well, n minus 4 squared would not be an increasing.
Yeah, when you do things like that, seeing that also parallel shape that in greatness rules.
But it's not a good rule.
Yeah, or like something that you, if you took like a parabola and shifted it up and to the right, then it would break the rule.
Right.
We just do it right, like.
That's because it starts,
X
conversion
minus
is all
four,
over,
X
n minus
minus
4
4
squared starts at 8, and it goes to 4.
I don't think we're supposed to
Yeah.
cover everything.
Yeah.
I heard that. It's not supposed to contain every possible series.
Wait, but then it just won't be by count.
These are increasing?
Yeah.
In other words,
Decreasing.
in other words, no, that's what this effect, it would just not be by count, it would just be a sequence.
Yeah.
If,
Not by count.
if we have an increasing function, sequence, the ratio would be bigger than 1. And if it was decreasing, less than 1.
So these tests can just fail to work.
Okay, so make sure you write down ratio test decreasing if that same ratio is less than 1. Derivative tests are favorite. If we take the derivative and the derivative is greater than 0 for all of the positive integers, then we have an increasing sequence. Tyler?
I was just thinking.
Okay. I don't know if you're thinking of. Yeah.
Where's the point in having rules that only work sometimes? Converting them.
Well, if the rules don't work, then we don't have an increasing or decreasing.
The reason I asked is because
You could test.
Okay.
Oh, wait.
Well, you could have like an increasing then decreasing. So
that's
this is
why-
like always increasing or always decreasing.
Well, you could test a point with this and it would be true that it's increasing, and then you could test another point and be true that it's decreasing. That's what I was wondering is, you would test n values, you would have.
Well, this is like a sub n plus one and a sub n. Like, this isn't like the second term and third term. This is like you're plugging in n plus one and you're plugging in n.
Mhm.
Does that make sense?
Yeah, so at one value of n, it could be true, but then at another value of n, it could be false.
And that's why it's important to think about the domain of 1 to infinity. Is it true for that entire domain? Is that? Okay. So there's going to be a little bit of thought to it. Okay, is this true for all positive integers? Okay, derivative test, decreasing if our derivative is less than 0. Okay. Oh, and that's the 3 tests. For some reason I thought there was no.
Which do you think is the easiest one?
Depends on the situation. Derivative is probably, I don't know. I mean, derivative is what we're probably most comfortable with, right? We're going to do the sequence n over n plus 1 for all 3. Okay. That's like the first thing that we looked at, right? That was one of the first sequences, and what does it look like it is? 1/2, 2/3, 3/4, 4/5.
Always increasing.
Okay. So, write down that this is the sequence that we're working with. We're first going to use the difference test. Okay, the difference test, we need to look at a sub n plus 1 and subtract a sub n. So a sub n plus 1 would be n plus 1 over n plus 2. And then we're going to subtract a sub n. You're all excited, right?
Yes.
Okay? Common denominators, right? We have n squared plus 2n plus 1 over our common denominator. And we're subtracting n squared plus 2n over our common denominator. So when we subtract, what are we left with in the numerator? 1. Thank you. For all positive integers, 1 to infinity, how will this compare to 0 every single time? Which means we have an increasing sequence. Okay. Now, if this was only true from 3 and above, then we would only have an increasing sequence from 3 to infinity. It wouldn't always be increasing.
And that also means that the entire thing is not monotonic. Because it's
Depending on what those first couple are. So if your sequence is like 1, 1, 2, 3, 4, 5, you know what I mean? Then that would be monotonic. So you'd have to consider what you
It could be just not decreasing.
Right. depending on what you have. All right, let's look at the ratio test. I actually kind of like the ratio test. So the ratio test, we have to look at a sub n plus 1 over a sub n. Okay, so a sub n plus 1 is n plus 1 over n plus 2, dividing by a sub n.
Can we just use one of these every time?
Oh yeah, you're not going to do all three. Oh yeah. Oh. So you're going to take, we all know that when we divide, it means we're multiplying by the reciprocal. So we have n squared plus 2n plus 1 all over n squared plus 2n. Now, this test is not useful if you can't look at the fraction and easily determine whether it's bigger or less than 1, okay? There's going to be times where you're like, I have no idea how to tell this, if that's not efficient, okay? But clearly, we can see that the numerator will always be 1 larger than the denominator. So we have a fraction larger than 1, which means we're increasing. And last but not least, let's do the derivative test. So basically you want to write that your function f of n is n over n plus 1. So our derivative. The derivative of n times n plus 1 minus n times the derivative of n plus 1, right? Give us that numerator. All over n plus 1 the quantity squared. Huh. This is our derivative. From 1 to infinity, what's good about this derivative? It's positive. And if a derivative is positive, that means our function, or in this case sequence, is increasing.